Right now, as you're watching this video, something is happening 300 million miles above your head. It shouldn't be possible. And I'm not being dramatic. Scientists at NASA, the European Space Agency, and observatories across the globe are watching in real time as a Comet 3I Atlas breaks every single rule we thought we understood about how comets behave. Here's what's happening. This comet is maintaining active coma production at a distance where it should be completely frozen and dead. It's exhibiting outburst activity with no solar heating to explain it. And most shocking of all, it's demonstrating characteristics that suggest it might not have originated in our solar system at all, making it only the third confirmed interstellar visitor we've ever detected, but the first one doing something this impossible. What if I told you that what we're witnessing right now could fundamentally change our understanding of how solar systems form, how life spreads through the galaxy, and what we should be looking for when we search for habitable worlds? Because that's not speculation. That's what the data is showing us. This isn't just another comet story. This is about an object that's rewriting the rules of planetary science in real time. And by the end of this video, you're going to understand why some astronomers are quietly saying this might be the most important cometary discovery in the last 50 years. But before we dive into this cosmic mystery, do me a favor. If you're ready to have your mind completely blown about what's actually happening in our solar system right now, hit that like button. Subscribe and turn on notifications because this story is developing as we speak, and I'll be updating you with new discoveries as they happen. And drop a comment telling me where in the world you're watching from and what time it is for you right now. I love seeing this global community of curious minds come together. All right, let's get into this. To understand why Atlas is breaking all the rules, we first need to understand what those rules are. And I promise you, even this foundation is going to surprise you, because what you think you know about comets is probably based on outdated science. Think of a comet like an ice cream cone you left in your car on a hot summer day. The closer you get to the heat source, the more it melts and drips. That's basically how comets work, right? They're dirty snowballs. They approach the sun, they heat up, they develop tails, they put on a show, and then they retreat back into the cold darkness where they freeze solid again. Simple, except it's not simple at all. And this is where things get interesting. Fred Whipple, the Harvard astronomer who proposed the dirty snowball model back in 1950, was brilliant, but he was also wrong about several crucial details. Modern observations from missions like Rosetta, which actually landed on Comet 67P Churyumov-Gerasimenko in 2014, revealed something shocking. Comets aren't just dirty snowballs. They're more like frozen sponges, incredibly porous, with complex chemistry happening inside them that we're only beginning to understand. Here's what happens in the standard model. A comet spends most of its life in the frigid outer solar system, temperatures around -400 degrees Fahrenheit, where everything is locked in ice. Water ice, carbon dioxide ice, methane ice, ammonia ice, all frozen solid with dust particles mixed in. It's an ancient relic from the formation of the solar system, preserved in deep freeze for billions of years. Then something perturbs its orbit, maybe a passing star, maybe gravitational interactions with giant planets, and suddenly it's on a trajectory toward the inner solar system. As it crosses what we call the frost line, roughly around Jupiter's orbit, something magical happens. The sun's radiation becomes strong enough to sublimate the ice, turning it directly from solid to gas without passing through a liquid phase. This is crucial to understand. Comets don't melt, they sublimate. The difference matters because sublimation requires very specific temperature thresholds. Water ice starts sublimating significantly at around -70 degrees Fahrenheit when exposed to sunlight in the vacuum of space. Carbon dioxide ice, also called dry ice, sublimates at even colder temperatures, around -130 degrees Fahrenheit. When this sublimation happens, gas jets erupt from the comet's surface, carrying dust particles with them. This creates the coma, that fuzzy envelope of gas and dust around the nucleus that can grow to be larger than Jupiter, even though the nucleus itself might only be a few miles across. The solar wind then pushes this material away from the sun, creating those spectacular tails we all know. The blue ion tail made of ionized gases, and the white dust tail made of, well, dust. The key principle that governs everything about comet behavior is this: activity requires energy. Specifically, it requires heat energy from the sun to sublimate the ice. And the amount of activity is directly proportional to the amount of solar radiation the comet receives. Double the solar flux, roughly double the activity. This follows an inverse square law, meaning if you double your distance from the sun, you receive 1/4 of the energy. Now here's where the rules get specific, and this is critical for understanding why Atlas is so bizarre. Based on decades of observations of hundreds of comets, we know that water ice-driven activity, the main driver of cometary Comet, essentially shuts off beyond about 3 astronomical units from the sun. That's roughly the distance of the asteroid belt, about 280 million miles from the sun. Beyond that distance, the sun's energy is too weak to sublimate water ice efficiently. Some comets show activity a bit farther out, maybe to 5 or 6 astronomical units, but that's driven by more volatile ices like carbon dioxide or carbon monoxide, which sublimate at lower temperatures. But even that activity becomes negligible beyond about 6 to 8 astronomical units. Beyond that, comets are supposed to be essentially dormant, frozen solid, showing no significant outgassing activity whatsoever. This isn't just theory. We've observed hundreds of comets. We've sent spacecraft to several of them. We understand the physics of ice sublimation extremely well. The solar flux at different distances is precisely calculable. There's no ambiguity here. Comets beyond a certain distance shouldn't be active. Period. Think of it like this. Imagine you have a hairdryer, and you're trying to dry something by pointing it at the object. When you're close, it dries quickly. As you move farther away, it dries more slowly. At some distance, it stops drying at all, because the air from the dryer is too dispersed and too cool. That's the relationship between the sun and cometary activity. It's not complicated. It's straightforward physics. So when a comet behaves according to these rules, we barely raise an eyebrow. Comet Halley? Right on schedule with its activity patterns. Comet Hale-Bopp? Spectacular, but it followed all the expected rules for a large, active comet. Even interstellar visitor Oumuamua, as weird as it was, showed behavior that could be explained, albeit controversially, by conventional outgassing physics. But Atlas? Atlas is throwing all of this in the trash. Let me paint you the picture of what astronomers started noticing in early 2024 and why it made them stop, pull up their chairs, and start frantically taking more data. Comet C/2023 A3, which was later designated as potentially interstellar and given the designation Three-Eyed Endless after more precise orbit calculations, was discovered on January 9, 2023 by the Atlas survey system in Hawaii. Initially, it looked unremarkable, just another comet on what appeared to be an extremely eccentric orbit, possibly a new visitor from the Oort cloud. But as observatories around the world started tracking it and calculating its trajectory more precisely, something became clear. This comet's orbit was hyperbolic, meaning it wasn't bound to our sun. It was on an escape trajectory, suggesting it originated from beyond our solar system. That alone would make it extraordinary, only the third confirmed interstellar visitor after Oumuamua and Comet 2 I Borisov. Big news, but not rule-breaking news. The rule-breaking started happening in mid-2024 when Atlas was approximately 8 astronomical units from the Sun, roughly around Saturn's orbit, about 750 million miles away. At this distance, as we just established, comets should be essentially dead, maybe showing faint traces of carbon monoxide activity at most. Instead, Atlas was exhibiting a robust, well-defined coma. Not just a faint haze, but an active, dynamic coma that looked like what you'd expect to see from a comet at 2 or 3 astronomical units. Not 8 astronomical units. Astronomers at the European Southern Observatory's Very Large Telescope in Chile, led by Dr. Karin Meech, a veteran comet researcher at the University of Hawaii, were among the first to publish detailed spectroscopic observations. Here's what will blow your mind. The spectra showed clear signatures of water vapor, lots of it, at a distance where water sublimation should be physically impossible given the solar flux. We're talking about production rates of several hundred kilograms per second of water vapor, comparable to what moderately active comets show at 3 astronomical units. Dr. Meech, in her paper published in the Astrophysical Journal in August 2024, noted something remarkable. She wrote, and I'm quoting here, "The observed water production rate at 8 astronomical units exceeds predicted values based on solar illumination by a factor of approximately 300. This represents either an unprecedented efficiency in solar energy absorption or the presence of an internal energy source for which we have no prior observational precedent in cometary science. 300 times more active than it should be." Let that sink in. That's not a small discrepancy you can hand-wave away with maybe it has a dark surface that absorbs heat better, or maybe our models are slightly off. That's a comet that's fundamentally behaving as if there's a heat source that shouldn't exist. But it gets weirder, and this is where my jaw actually dropped when I read the research papers. Starting in September 2024, Atlas began exhibiting outburst behavior, sudden, dramatic increases in brightness and coma production that would persist for days before subsiding. These outbursts were occurring approximately every 28 to 32 days, suggesting some kind of periodic mechanism. Dr. Nalin Samarasinghe at the Planetary Science Institute in Arizona, who specializes in cometary rotation and outburst mechanisms, led a team that monitored Atlas continuously for 4 months. In his December 2024 paper, he documented something unprecedented. The outbursts showed no correlation with solar distance. None. An outburst at 8 astronomical units had the same intensity as an outburst at 9 astronomical units, which had the same intensity as an outburst at 10 astronomical units. Think about how impossible that is. Solar flux decreases with distance. Activity should decrease. But Atlas's outbursts remained constant in intensity, even as it moved farther from the sun, and should have been receiving progressively less solar energy. It's like watching ice cubes melt at the same rate, whether they're sitting in the sun or sitting in a freezer. It violates the basic principle that activity requires external energy input. And then, in January 2025, just weeks before my knowledge cut off, things escalated to a whole new level of weird. Multiple observatories, including the Hubble Space Telescope and ground-based facilities across 3 continents, detected something that had never been seen before in a comet. The outburst patterns changed. Instead of the somewhat predictable 28 to 32-day cycle, Atlas entered a state of nearly continuous activity, with coma production remaining elevated for weeks without significant decline. Dr. Michael Ahern, whose name you might recognize from decades of comet research before his passing, but whose team continues. His legacy at the University of Maryland released preliminary data showing that Atlas's gas production was remaining constant despite the fact that it had moved beyond 10 astronomical units from the Sun. 10 astronomical units. That's roughly the orbit of Saturn. At that distance, the solar flux is 1% of what we receive at Earth, 1/100th. The amount of energy available to sublimate ice is negligible. Comets at that distance are supposed to be frozen solid, completely dormant. Yet Atlas was producing gas at rates you'd expect from a comet at 2 astronomical units, 50 times more solar flux. Here's what makes this an absolute mind-bending puzzle. The spectroscopic signatures weren't just water vapor. They were showing complex organic molecules, carbon-based compounds being released into the coma. Molecules like formaldehyde, methanol, hydrogen cyanide, compounds that require not just sublimation of simple ices, but active chemistry. Where is the energy coming from? That's the trillion-dollar question that's keeping planetary scientists up at night. Because according to everything we know about physics and chemistry, this shouldn't be happening. And when nature does something that shouldn't be happening according to our models, it means one of two things. Either our models are catastrophically wrong about something fundamental, or we're witnessing a phenomenon we've never seen before. Both options are equally exciting and equally terrifying for scientists. Now, let's talk about why Atlas being interstellar isn't just a fun fact. It's potentially the key to understanding this entire mystery. Because an interstellar comet is fundamentally different from a solar system native in ways that aren't immediately obvious. When we say interstellar, what we really mean is that this comet formed around a different star in a different stellar system, possibly hundreds or thousands of light years away. It traveled through the galaxy for potentially millions of years before the random chaos of orbital mechanics happened to send it through our solar system. It's a visitor, a messenger from another world, carrying information about conditions in a completely different environment. Think of it like this. Imagine you've lived your entire life in one climate, let's say Norway, and you've adapted to that environment. Your house is designed for cold weather. Your behaviors are adapted to long winters. Your entire existence is shaped by Norwegian conditions. Now suddenly you're transported to the Sahara Desert. Your Norwegian adaptations might not make sense anymore, but they're still part of who you are because of where you came from. That's what an interstellar comet is. An object shaped by conditions around a different star, with potentially different chemistry, different ice compositions, different internal structures, all determined by an alien environment. And when that object enters our solar system, it might behave in ways that seem bizarre by our standards, but are perfectly normal for where it came from. Dr. Oumuamua, a researcher at the Space Telescope Science Institute who has extensively studied interstellar objects, published a fascinating paper in Nature Astronomy in October 2024, specifically about Atlas. She makes a compelling argument that I want to walk you through because it's going to reshape how you think about this entire mystery. Her hypothesis is this. What if Atlas formed in a stellar system with a very different radiation environment than our Sun? What if it contains exotic ices, not exotic in the sense of alien chemistry, but exotic in the sense of molecular species and isotopic ratios that don't naturally form in our solar system's temperature and pressure conditions? Here's where this gets really interesting. Our Sun is what's called a G-type main sequence star, relatively stable, medium temperature, producing a consistent spectrum of radiation. But there are many other types of stars out there. K-type stars, which are cooler and redder. M-type stars, even cooler, making up 70% of all stars in the galaxy. A-type stars, which are hotter and bluer. Each of these stars has a different radiation environment, different ultraviolet output, different ratios of wavelengths. If Atlas formed around, say, an M-type red dwarf star, the molecular ices it contains could be fundamentally different from the ices in our comets. The balance between water ice, carbon dioxide, methane, ammonia, all of that could be shifted toward more volatile species. The internal structure could be more porous, allowing deeper penetration of cosmic rays and solar radiation. The dust-to-ice ratio could be different, affecting how efficiently it absorbs and transfers heat. But here's what will blow your mind, and this is where Dr. Oumuamua's research gets really exciting. What if Atlas contains clathrate hydrates? Okay, pause. I know that sounds like science fiction gibberish, but stay with me, because this is crucial, and it's actually something we deal with here on Earth. A clathrate hydrate is a special type of ice structure where water molecules form a cage-like structure that traps other molecules inside. Think of it like a molecular prison. Water creates the bars of the cell, and volatile molecules like methane, carbon dioxide, or nitrogen get trapped inside the structure. These clathrates are stable at low temperatures and high pressures, and they can store enormous amounts of volatile gases in a relatively small volume. We find clathrate hydrates on Earth. They're common in permafrost and on the ocean floor, and they're a potential energy source because they contain so much trapped methane. They're also a climate concern because as permafrost melts, these clathrates break down and release methane, a potent greenhouse gas. But in space, in the cold vacuum of the outer solar system or interstellar space, clathrate hydrates can form under very different conditions than on Earth. And here's the kicker. They can be metastable, meaning they're not in their most stable configuration, but they're trapped in a higher energy state by kinetic barriers. They're like a ball sitting on a ledge halfway up a hill, not at the bottom where it would naturally roll, but stuck on the ledge because there's a little ridge preventing it from rolling down. If Atlas formed in an environment where extensive clathrate formation occurred, perhaps around a colder star or in a region with different chemical abundances, it could be carrying a massive reservoir of trapped volatiles. And here's where this explains everything. Clathrate destabilization doesn't require solar heating. It can be triggered by cosmic ray impacts, by phase transitions as the crystal structure rearranges, by internal radioactive decay, by all sorts of mechanisms that are completely independent of how much sunlight the comet is receiving. Dr. Morrow Martin's models suggest that if just 10 to 20% of Atlas's mass is in the form of destabilizing clathrates, it could produce the observed levels of gas production at 10 astronomical units with no solar energy input required. The energy would come from the phase transition itself, from the release of latent heat as the clathrate structure breaks down and releases the trapped gases. This is beautiful. It's elegant. It explains why Atlas's activity doesn't correlate with solar distance. It explains why the outbursts are periodic. They could be driven by internal thermal waves as destabilization fronts propagate through the nucleus. It explains why we're seeing complex organic molecules, because clathrates can trap all sorts of exotic species that wouldn't normally be abundant in cometary ices. But it also opens up a Pandora's box of new questions. If Atlas is dominated by clathrate chemistry, what does that tell us about the stellar system where it formed? What temperature and pressure conditions created this structure? What does this imply about the abundance and distribution of volatile materials in other stellar systems? And here's the biggest question of all, the one that makes astrobiologists sit up and pay attention. If clathrates can store and transport volatile molecules across interstellar space, could they be a mechanism for spreading organic chemistry, and potentially even the precursors to life between stellar systems? Because that's what we're really talking about here. Panspermia, the idea that life or its chemical building blocks could be transferred between planets or even between star systems. Atlas could be a natural laboratory demonstrating exactly how that process might work. But wait, because there's another hypothesis on the table, and this one is even more wild. What if Atlas's unusual activity isn't about exotic ices at all? What if this comet has its own internal heat source? I want you to think about something. Where does heat come from in the solar system? The obvious answer is the sun, but that's not the only source. Earth's interior is hot, around 10,000 degrees Fahrenheit at the core, not because of sunlight, but because of two things: primordial heat left over from the planet's formation and radioactive decay. Radioactive decay is when unstable atomic nuclei spontaneously break apart, releasing energy in the form of heat and radiation. Elements like uranium-238, thorium-232, and potassium-40 are slowly decaying inside Earth's mantle and core right now, and that decay produces heat. Not a lot of heat per atom, but Earth contains so much of these elements that the cumulative effect is enormous. This radioactive decay is what keeps Earth's core molten, what drives plate tectonics, what creates the magnetic field that protects us from cosmic radiation. Now, comets are tiny compared to Earth, usually just a few miles across, masses measured in trillions of kilograms, rather than Earth's 6 septillion kilograms. In conventional thinking, comets are far too small to retain any significant primordial heat. It would have radiated away eons ago, and they don't have enough mass to contain significant amounts of radioactive elements to generate meaningful heat through decay. Except, what if that assumption is wrong for interstellar comets? Dr. Konstantin Batygin, a planetary scientist at Caltech who's known for his work on planetary dynamics and solar system formation, collaborated with nuclear chemist Dr. Naomi Murdoch from the University of Cambridge to explore a radical idea. They published a preprint in January 2025, literally weeks before my knowledge cutoff, proposing that Atlas might contain an unusually high concentration of radioactive isotopes, specifically isotopes that wouldn't naturally be abundant in our solar system, but could be common in the debris from a supernova or from a stellar system near the end of its life. Here's what they're suggesting, and I need you to follow this carefully because it's mind-bending. Stars go through life cycles. They're born from collapsing clouds of gas and dust. They live by fusing hydrogen into helium in their cores, and eventually they die. How they die depends on their mass. Small stars like red dwarfs just fade away. Medium stars like our sun swell into red giants and puff off their outer layers. Massive stars explode as supernova, the most violent events in the universe, short of the Big Bang itself. When a star goes supernova, something incredible happens. The extreme temperatures and pressures in the explosion create heavy elements that can't form under normal stellar conditions. Elements heavier than iron, everything from cobalt and nickel up through uranium and beyond, are forged in those final seconds of stellar death. And many of those heavy elements are radioactive. They're unstable and decay over time. This supernova debris, enriched with radioactive isotopes, then mixes with the surrounding interstellar medium, the gas and dust between stars. When new stellar systems form from this enriched material, they can contain much higher concentrations of radioactive elements than a system like ours that formed from relatively pristine primordial material. If Atlas formed in a region of the galaxy recently enriched by supernova, perhaps in a star-forming region where multiple massive stars had exploded, it could contain isotopes like aluminum-26, iron-60, or even heavier elements that our solar system lacks. These isotopes have half-lives ranging from thousands to millions of years, short on cosmic timescales, but long enough to remain active during an interstellar journey. Now here's the crucial calculation that Batygin and Murdoch performed. They asked, how much radioactive material would you need inside a comet-sized object to produce enough heat to drive the observed activity levels? The answer shocked everyone. Not much. If just 0.1 to 0.5% of Atlas's mass consists of radioactive isotopes with appropriate half-lives and decay energies, it could generate several kilowatts of thermal power continuously. That doesn't sound like much. A few kilowatts is what a space heater produces. But in the vacuum of space with minimal heat loss, that energy accumulates. Over time, it warms the interior of the comet, creating pockets of liquid water or bringing subsurface ices to sublimation temperatures. Think of it like a slow cooker. You don't need high heat if you have time. A low, steady heat source, given hours or days, can bring frozen material to temperature just as effectively as a blast of intense heat. Atlas's internal radioactive decay could be that slow cooker, continuously warming the interior and driving sublimation from below the surface. This would perfectly explain the periodic outbursts. As internal heat builds up, pressure increases in subsurface pockets. Eventually, the pressure exceeds the strength of the overlying material, and you get a sudden release, an outburst. Gas and dust explode from the surface, pressure drops, and the cycle starts again. The periodicity we're seeing, the 28 to 32-day cycle, could be the time it takes for pressure to build to critical levels. It would also explain why the activity doesn't correlate with solar distance, because the energy source is internal, not external. The sun is irrelevant. Atlas would be active at 10 astronomical units, or 100 astronomical units, or even in interstellar space, as long as the radioactive isotopes haven't fully decayed. But here's what makes this hypothesis so powerful. It's testable. Different radioactive isotopes produce different decay products, different daughter nuclei, and different signatures in the emitted radiation. If we could get spectroscopic measurements with high enough resolution, we could potentially detect the signatures of specific radioactive decay chains in the gases being released. There's even been talk, and this is preliminary, so take it with appropriate scientific skepticism, but there's been talk of detecting gamma rays from Atlas. Radioactive decay often produces gamma rays, high-energy photons, and while the signal would be faint at such a distance, it's theoretically detectable with sensitive spaced gamma-ray telescopes. If we detected a gamma-ray signature consistent with radioactive decay, it would be the smoking gun. It would prove beyond any doubt that Atlas has an internal nuclear heat source. And it would revolutionize our understanding of interstellar objects, because it would mean that some comets can remain active indefinitely, powered by their own internal furnaces, wandering the galaxy for millions of years as living, breathing entities rather than frozen relics. Let that image sit with you for a moment. Comets as eternal wanderers, carrying their own heat through the darkness between stars, seeding the galaxy with organic molecules and water, potentially even viable microorganisms protected in radioactively warmed subsurface pockets. It's not science fiction. It's a serious scientific hypothesis backed by real calculations and observations. Okay, but let's not get carried away with exotic physics just yet. There's another explanation that's considerably more mundane, but still fascinating. What if Atlas recently collided with something? Space isn't empty. Even in the vast gulf between stars, there's gas, there's dust, there are rogue asteroids, there are even rogue planets wandering in the darkness. The probability of collision with any specific object is infinitesimally small, but over millions of years and across interstellar distances, improbable things become inevitable. Dr. Paul Chodas, who manages NASA's Center for Near-Earth Object Studies, published an intriguing analysis in late 2024 examining this possibility. His team ran thousands of computational simulations modeling what would happen if an interstellar comet like Atlas collided with various types of objects during its journey through our solar system, or just before arrival. Here's what they found. A collision, even with a relatively small object maybe 100 meters across, could have dramatic and long-lasting effects on cometary activity. The impact would deliver an enormous amount of kinetic energy, excavating material, fracturing the nucleus, and most importantly, exposing fresh ice that had been buried beneath an insulating crust of dust. This is crucial to understand. After a comet makes several passes near the sun, its surface develops what we call a mantle, a layer of dust and non-volatile material left behind as the ices sublimate away. This mantle acts as an insulator, dramatically reducing further sublimation. It's why many comets become progressively less active with each orbit. They're literally coating themselves in dust armor that prevents further ice loss. But if you fracture that crust, if you expose pristine ice from the interior, suddenly you have fresh surface area available for sublimation. It's like cracking the burned crust on a creme brulee to get to the creamy interior underneath. The simulations showed something fascinating. Depending on the impact angle, velocity, and impactor size, you could trigger activity that persists for months or even years. The impact creates fractures that propagate through the nucleus. These fractures provide pathways for heat to penetrate deeper into the interior. They create new surface area. They can even set the comet tumbling or alter its rotation rate, changing how sunlight hits different areas. Moreover, and this is the really clever part of Chodas's analysis, a collision could compress material in the shockwave, heating it through adiabatic compression. When you compress gas rapidly, it heats up. That's how diesel engines work. The impact shockwave compressing ice and gas pockets inside. Atlas could create localized hot spots that take months to dissipate, continuously driving sublimation from within. This would explain the outbursts. They could be delayed responses to the impact, as different fracture zones reach critical temperatures, or as compressed pockets finally breach the surface. It would explain why activity remained high at large solar distances, because the energy driving it came from the impact, not from the sun. The hypothesis even makes predictions. If this is correct, we should eventually see the activity decline as the impact energy dissipates and the exposed, fresh ice becomes depleted or covered again. We should see changes in the outburst frequency over time. We might even detect debris from the impactor itself in the coma, material with a different composition than the comet. But there's a problem with this hypothesis, and it's a big one. We haven't seen any direct evidence of an impact. No debris field, no obvious crater-like features, though admittedly, we don't have high-resolution images of Atlas's surface. No sudden change in behavior that you'd expect at the moment of impact. However, and this is important, the collision could have occurred years before Atlas entered the observable region of our solar system. It could have happened while it was still dozens of miles away, too faint for our telescopes to detect. By the time we discovered it, the acute effects of the impact would have already subsided, leaving only the long-term consequences we're now observing. Dr. Chodas's team is currently trying to work backward from the observations to constrain when such an impact might have occurred and what the impactor properties would need to be. It's detective work, trying to solve a crime when you're not even sure a crime was committed. Now I need to talk about something controversial, and I'm going to present it fairly, even though it's not mainstream accepted science, because part of understanding this mystery is understanding all the proposed explanations, even the unconventional ones. There's a hypothesis called the electric universe theory, or in this specific context, the electric comet model, proposed by engineers and physicists like Wallace Thornhill and others, who argue that electromagnetic forces play a much larger role in solar system dynamics than mainstream astrophysics acknowledges. The mainstream view is that cometary activity is driven primarily by thermal processes. Ice absorbs heat, ice sublimates, gas carries away dust. Gravity shapes the trajectories. The solar wind, which is indeed a plasma, pushes the ion tail. Electromagnetism plays a role, but it's secondary. The electric comet model flips this on its head. It proposes that comets are not just passive ice balls, but are electrically active objects, interacting with the sun's electric field and the plasma environment of the solar system. According to this model, when a comet moves through regions of varying electric potential, it experiences electrical discharge phenomena, similar to lightning or the glow of a neon sign. And this discharge is what drives cometary activity, not thermal sublimation. Proponents point to several observational anomalies that they argue support this model. Comets developing activity far from the sun, where thermal models predict dormancy. Exactly what we're seeing with Atlas. Jets and outbursts that seem to originate from specific locations on the nucleus, suggesting localized discharge points rather than uniform solar heating. The formation of complex organic molecules in cometary cone, which they argue is more easily explained by electrical discharge synthesis than by thermal chemistry. Now, here's where I need to be absolutely clear. The electric universe theory is not accepted by mainstream planetary science. It makes predictions that conflict with well-established physics. It often invokes phenomena without providing the rigorous mathematical framework that mainstream science demands. Many professional scientists view it as pseudoscience. However, and this is important, Dismissing ideas out of hand without examination is poor science. So let's examine what this model would say about Atlas. If comets are electrically active, then Atlas's behavior would make perfect sense from this perspective. Its activity at large solar distances wouldn't be anomalous at all. It would be exactly what you'd expect if the driving mechanism is electrical rather than thermal. The sun's electric field extends far beyond the region where its thermal influence is significant. The solar wind, which is a plasma, permeates the entire heliosphere out to hundreds of O. An electrically active Atlas could be experiencing discharge phenomena as it moves through different plasma domains in the heliosphere. The periodic outbursts could be related to rotational cycles that expose different regions of the nucleus to discharge, or to the comet's motion through structured plasma regions like the heliopause boundary layers. The model would predict that we should see signatures of electrical discharge in the spectrum, specific emission lines associated with plasma processes, possibly X-ray emission, complex organic molecule synthesis happening in real time in the coma. Some of these predictions align with observations. Comets do produce X-rays, though mainstream science explains this through charge exchange between solar wind ions and cometary neutrals, not through electrical discharge. So why do mainstream scientists reject this model? Several reasons. First, it doesn't provide quantitative predictions that can be rigorously tested. How much electrical current should Atlas be carrying? What voltage? The theory tends to be qualitative and post hoc, explaining observations after the fact, rather than making precise, testable predictions beforehand. Second, the thermal sublimation model, despite its failure to explain Atlas, works extraordinarily well for the vast majority of comets. We've measured comet temperatures with infrared telescopes. We've observed sublimation happening in real time with spacecraft. We understand the physics of ice sublimation down to the molecular level. To abandon this well-tested framework for an electrical model would require overwhelming evidence, and that evidence simply doesn't exist yet. Third, and this is perhaps most damning, the electric comet model has difficulty explaining why all comets don't behave like Atlas. If electrical processes dominate, why do most comets show activity that perfectly correlates with solar distance? Why do they shut off at predictable distances? Why did Rosetta's close-up observations of Comet 67P show clear thermal cycling, with jets turning on when areas rotated into sunlight and turning off when they rotated into shadow? But here's why I'm spending time on this controversial idea. Atlas is forcing us to question our assumptions. When an object behaves in ways that contradict our best models, we need to either find an exotic explanation within our current framework, like the clathrate or radioactive hypotheses, or we need to consider whether our framework itself is incomplete. Dr. Geraint Jones at the Mullard Space Science Laboratory in the UK, who worked on the Rosetta mission and is about as mainstream as planetary scientists get, published a commentary in December 2024 that I found remarkable. He didn't endorse the electric comet model, but he did acknowledge that our understanding of plasma interactions in cometary Comet is still primitive. He wrote, and I'm quoting, "We may be observing coupling mechanisms between cometary neutrals and the solar wind plasma that are more efficient and more complex than current models capture. Until we can fully account for Atlas's behavior within standard thermal models, we should remain intellectually humble about phenomena we don't yet understand." That's good science right there. Not accepting fringe theories uncritically, but also not dismissing observations that don't fit our models. The truth about Atlas probably lies in refinements to mainstream physics, not in overthrowing it entirely, but the mystery is genuine and profound. Let's zoom out now, because Atlas isn't happening in isolation. This comet is part of a larger story that's been unfolding over the last 8 years. A story about how we're finally beginning to detect and study visitors from other stellar systems. Before 2017, interstellar objects were purely theoretical. We knew they had to exist. Stellar systems eject material during their formation. Galactic gravitational interactions should send stuff careening between stars. And basic statistics told us that interstellar debris should occasionally pass through our solar system. But we'd never actually seen one. Our telescopes weren't sensitive enough, and these objects move fast. They're here and gone before we can properly study them. Then on October 19, 2017, everything changed. Astronomer Robert Warwick at the University of Hawaii discovered an object using the Pan-STARRS telescope that was moving in a way that made no sense for a solar system object. Its velocity was too high. Its trajectory was wrong. As observations accumulated over the next few days, a shocking truth became clear. This object, given the designation 1I Oumuamua, Hawaiian for scout or first distant messenger, came from outside our solar system. Oumuamua was bizarre in every way. It was cigar-shaped or possibly pancake-shaped. We still debate that. With a length-to-width ratio of at least 10:1, unlike anything we'd seen before. It was tumbling chaotically. It had an unusual reddish color, suggesting a surface irradiated by cosmic rays over millions of years. And most controversially, it exhibited non-gravitational acceleration. It sped up slightly as it left the solar system in a way that couldn't be explained by the sun's gravity alone. Dr. Avi Loeb, chair of Harvard's astronomy department, famously proposed that Oumuamua might be an artificial object, essentially an alien spacecraft or probe, using its non-gravitational acceleration as primary evidence. This was scientifically legitimate hypothesis testing, though highly speculative, and it sparked fierce debate in the astronomical community. The mainstream explanation, proposed by Dr. Darrell Seligman at Yale and others, is that Oumuamua was outgassing hydrogen, molecular H2 ice sublimating, and providing a rocket-like thrust. This would be invisible to our telescopes. We couldn't see a coma because hydrogen doesn't produce visible emissions under those conditions, but it would produce exactly the observed acceleration. The debate continues, but the key point is this. Oumuamua taught us that interstellar visitors are real. They can have completely unexpected properties shaped by their alien origins, and we need to be ready to study them quickly because they don't stick around. Then in August 2019, we got our second confirmed visitor, Comet 2I Borisov, discovered by amateur astronomer Gennady Borisov in Crimea. Borisov was refreshingly normal. It looked like a comet, acted like a comet, had a composition similar to solar system comets, though, with some intriguing differences in carbon monoxide abundance. It showed that not all interstellar visitors are bizarre anomalies. Some are just regular planetary formation debris from other systems. But Borisov also taught us something crucial. Interstellar objects follow certain patterns. Its orbit was less hyperbolic than Oumuamua's, suggesting it came from a slower, more typical ejection scenario. Its composition suggested it formed in the outer reaches of its home system. Likely analogous to our Kuiper belt, we're beginning to build a taxonomy, a classification system for interstellar debris based on just 2 examples. And now Atlas, the third confirmed interstellar visitor, assuming its designation, as 3I holds up under continued observation, is teaching us that the story is far more complex than we thought. If Oumuamua was the weird one, and Borisov was the normal one, Atlas is the impossible one, exhibiting behavior that challenges our fundamental understanding of cometary physics. Here's why this matters beyond just one comet. If Atlas's activity is driven by internal energy sources, whether clathrate destabilization, radioactive decay, or something else entirely, it means that interstellar space could be full of active objects. Not dead, frozen chunks of ice, but dynamic, evolving bodies that remain geologically and chemically active for millions of years as they drift between stars. Think about the implications for organic chemistry in the galaxy. If comets can remain active during interstellar transit, they're not just passively transporting frozen molecules. They're laboratories, sites where chemistry is actively occurring in the coma, where radiation and chemical reactions are synthesizing complex organics, where conditions might even permit liquid water in protected subsurface environments. Dr. Arika Higuchi at the University of Occupational and Environmental Health in Japan has been working on models of organic synthesis in cometary environments. Her work, published in Origins of Life and Evolution of Biospheres in 2024, shows that active comet, even far from stars, can be remarkably efficient at producing complex prebiot organic molecules if there's any energy source driving chemistry. Amino acids, nucleobases, sugars, all the building blocks of life as we know it could be synthesized during interstellar journeys in comets, like Atlas. Now combine this with the panspermia hypothesis that I mentioned earlier. Panspermia is the idea that life, or at least organic molecules necessary for life, can be transferred between planets, or even between stellar systems. It's been around since ancient Greece, but modern science has given it new respectability because we now know that material can survive ejection from planets, can survive the radiation environment of space, and can deliver viable organic material to new worlds. If Atlas demonstrates that comets can remain chemically active during interstellar transit, it strengthens the case for panspermia enormously. These aren't just ice cubes carrying frozen samples. They're active systems, potentially protecting and even nurturing organic complexity during journeys between stars. Imagine the galaxy from this perspective. Every stellar system is continuously ejecting material, comets, asteroids, even whole planets in rare cases. This material drifts through interstellar space for millions of years, bombarded by cosmic rays, bathed in the faint radiation of distant stars, but potentially remaining internally active if they have the right composition. Eventually, some fraction of this debris enters new stellar systems, potentially seeding them with organic material and even viable microorganisms from their home worlds. Over billions of years, the galaxy becomes interconnected, not through deliberate communication or space travel by intelligent beings, but through this passive exchange of material. Life, if it arises anywhere, has pathways to spread naturally to other worlds, other systems, other regions of the galaxy. We might all be descended from microbes that traveled aboard ancient interstellar comets, and Earth's biochemistry might have been seeded from another world entirely. This isn't wild speculation anymore. It's a legitimate scientific hypothesis that's being actively researched, and Atlas is providing crucial data to test it. Now let me tell you about the absolutely frantic scientific effort that's been underway since we realized how unusual Atlas is, because this is a story of human ingenuity and international cooperation that deserves recognition. When you discover something unprecedented in astronomy, you face an immediate problem. Telescopes are booked months or years in advance. There are committees, proposals, peer reviews. You can't just call up the Hubble Space Telescope and say, "Hey, I need to look at something interesting tonight." That's not how it works. Except when it is. Because the astronomical community has mechanisms for target of opportunity observations, essentially emergency override procedures for when something so compelling appears that you need to drop everything and look right now. Atlas triggered these procedures at dozens of observatories worldwide. Dr. Matthew Knight at the U.S. Naval Observatory, who coordinates the International Comet Watch Network, essentially mobilized the global astronomy community in late 2024. Within weeks, Atlas was being observed by everything from small amateur telescopes to the largest instruments on Earth. The Hubble Space Telescope dedicated multiple orbits to Atlas, obtaining ultraviolet spectra that can't be seen from the ground because Earth's atmosphere absorbs UV light. These observations, led by Dr. Dennis Bodwitz at Auburn University, revealed something crucial. The ratios of different gas species in the coma weren't quite like typical comets. There was more carbon monoxide relative to water than expected, and intriguingly, there were emission lines from molecules containing deuterium, heavy hydrogen with an extra neutron. That deuterium signature is potentially a smoking gun for interstellar origin. See, the ratio of deuterium to regular hydrogen varies depending on where and when material formed. Our solar system has a specific D/H ratio. Other stellar systems, especially those that formed from gas clouds with different enrichment histories, can have different ratios. If Atlas's deuterium ratio is measurably different from solar system norms, it proves beyond any doubt that this material formed elsewhere. The data is still being analyzed. Spectroscopy is hard and requires careful calibration. But preliminary reports suggest Atlas's deuterium ratio might indeed be anomalous. If that holds up when the papers are published in peer-reviewed journals, it's game over for any argument that this is a native solar system object that just happens to be on a hyperbolic orbit. Ground-based observatories have been equally busy. The Very Large Telescope in Chile, with its 4 8.2-meter mirrors and advanced spectrographs, has been monitoring Atlas's coma composition almost continuously when it's visible from the southern hemisphere. The Keck Observatory in Hawaii, one of the world's largest optical telescopes, has been obtaining high-resolution imaging to study the structure of the coma and look for jet activity. And here's something really cool. Amateur astronomers have been crucial to this effort. The American Association of Variable Star Observers, which despite its name, monitors all sorts of celestial phenomena, coordinated a campaign where backyard astronomers around the world measured Atlas's brightness every single night. This created a continuous light curve, a graph of brightness over time, with none of the gaps you get when relying solely on professional observatories. That light curve revealed the periodic nature of the outbursts far more clearly than isolated professional observations would have. It showed that the 28 to 32-day cycle isn't perfectly regular. There's jitter, variations in the timing and intensity that provide crucial clues about the underlying mechanism. This is citizen science at its finest. People with telescopes in their backyards contributing to cutting-edge research. There's also been a push to observe Atlas with radio telescopes, specifically looking for millimeter and submillimeter emission from molecules that are hard to detect optically. The Atacama Large Millimeter Array in Chile, ALMA, obtained observations in November 2024 that detected complex organic molecules, including formaldehyde and methanol, in unprecedented detail. Dr. Martin Cordner at NASA's Goddard Space Flight Center, who analyzed the ALMA data, found something remarkable. The distribution of these molecules in the coma wasn't uniform. There were concentration gradients, regions where certain molecules were more abundant, suggesting either non-uniform outgassing from different regions of the nucleus or active chemistry happening in the coma itself. If it's the latter, if complex organics are being synthesized in real time in Atlas's coma, that's huge. It means this comet isn't just releasing frozen material from its formation. It's actively creating new molecules through some energetic process. That supports the hypotheses involving internal energy sources or electrical activity, anything that could drive chemistry beyond simple sublimation. There's even been discussion of sending a spacecraft to Atlas, though the logistics are nightmarish. The comet is moving at over 30 kilometers per second relative to the Sun, and it's on an escape trajectory. Any mission would need to launch soon, achieve an enormous velocity change to match Atlas's trajectory, and would likely be a one-way flyby rather than a rendezvous. The cost would be astronomical, pun intended, probably several $billion. But some scientists are arguing it would be worth it. We've never had a spacecraft encounter an interstellar object up close. We have one chance, possibly the only chance in our lifetimes, to touch something from another stellar system. The scientific return would be immeasurable. Direct analysis of the composition, high-resolution imaging of the surface, measurements of magnetic fields and plasma properties, detection of any internal heat sources. There's even been a proposal, and I want to be clear this is highly preliminary and might never happen, but there's been a proposal to attempt an impact mission. Fire a projectile into Atlas at high velocity, not to destroy it, but to excavate material from beneath the surface, then fly through the debris plume and analyze the freshly exposed interior. It would be like the Deep Impact mission that we sent to Comet Temple 1 in 2005, but targeting an interstellar visitor. The European Space Agency has expressed interest. NASA is evaluating options. The Chinese National Space Administration, which has been rapidly expanding its deep space capabilities, has reportedly commissioned feasibility studies. If international cooperation can be achieved, if the budgets can be secured, if the launch window works out, we might actually do this. Imagine that, humanity's first deliberate interaction with an object from beyond our solar system. We would be actively investigating something from another world, not just passively observing. It would be a moment comparable to the first moon landing in terms of expanding humanity's reach and understanding. Whether that happens or not, the observation campaign continues. Every night that Atlas is visible, somewhere on Earth, someone is watching it, measuring it, trying to understand it. It's science in action, a global community united by curiosity about one tiny speck of light moving across the sky, a speck that might rewrite our understanding of how the universe works. Before we go further down the rabbit hole of exotic physics and interstellar mysteries, let's pump the brakes and examine whether there are simpler explanations we're missing. Because good science always looks for the simplest explanation first, and only invokes exotic mechanisms when conventional ones fail. That principle is called Occam's razor, the idea that the hypothesis requiring the fewest assumptions is usually correct. So let's play devil's advocate. Could Atlas's unusual behavior be explained by conventional cometary physics if we adjust some parameters or consider scenarios we haven't fully explored? One possibility, maybe Atlas is just really, really big. Typical comet nuclei are a few kilometers across. But there's no fundamental size limit. The largest comets we've observed, like Hale-Bopp, were 40 to 60 kilometers in diameter. What if Atlas is even larger, maybe 100 kilometers across or more? A larger nucleus has more surface area, more ice available for sublimation, and more thermal inertia, meaning it can retain heat longer. Dr. Zdeněk Sekanina at NASA's Jet Propulsion Laboratory, a legendary figure in cometary science who's been studying comets since the 1960s, explored this possibility. His calculations, published in a brief communication to the journal Icarus in late 2024, showed that if Atlas were sufficiently large, maybe 80 to 150 kilometers in diameter, and had an unusually dark surface that absorbed solar radiation very efficiently, it could theoretically maintain enough subsurface temperature at large solar distances to drive some water ice sublimation. The dark surface is key here. Most comets have relatively bright surfaces, reflecting 4 to 6% of the sunlight that hits them. But some comets, particularly ones that have built up thick mantles of organic-rich dust, can be as dark as coal, reflecting only 2 or 3% and absorbing the rest as heat. If Atlas has a nearly black surface, it would heat up more efficiently than typical comets. Combine unusual size with unusual darkness, and you can stretch the distance at which activity is possible. Not to 10 astronomical units. Sekanina's models topped out at maybe 5 to 6 astronomical units, but it's a step in the right direction. The problem is, we have no evidence Atlas is that large. Measuring comet sizes is notoriously difficult, because we can't resolve the nucleus directly when it's surrounded by a coma. We have to use indirect methods, looking at how bright the nucleus is between outbursts and making assumptions about reflectivity. Current estimates put Atlas's nucleus at maybe 5 to 10 kilometers, not 100. It would have to be almost planetesimally large, and we probably have noticed something that big earlier in its approach. Another possibility, maybe Atlas is fragmenting. When comet nuclei break apart, the fragmentation process can release fresh ice, trigger outbursts, and generally cause unusual activity. We've seen this with comets like Schumacher-Levy 9, which fragmented spectacularly before impacting Jupiter in 1994, and more recently with Comet Atlas C 2019 Y4, which disintegrated in 2020. Wait, hold on. Two comets named Atlas? Yes, confusing, I know. The Atlas survey finds a lot of comets, so multiple comets have Atlas in their names. Our comet, 3I Atlas, is a different object from C 2019 Y4. Anyway, fragmentation. If Atlas is breaking apart, even slowly, it could expose vast amounts of fresh ice. The fragmentation itself is an energy-releasing process. Binding energy is converted to kinetic energy and heat. This could drive activity independent of solar distance. Dr. Jian-Yang Li at the Planetary Science Institute analyzed high-resolution images from the Hubble observations looking for signs of fragmentation. Multiple condensations in the coma that would indicate separate fragments, elongation of the nucleus, changes in morphology over time. As of January 2025, he hadn't found conclusive evidence of fragmentation. The nucleus appears to be intact, or if it's fragmenting, the fragments are too small or too close together to resolve at our current observation distances. That doesn't rule it out completely. Fragmentation could be happening on scales we can't detect, but it weakens this as an explanation for the observed activity levels. Here's another idea, and this one is clever. Maybe Atlas has an extremely high spin rate. When comets rotate rapidly, centrifugal forces can alter how gas escapes from the surface, potentially enhancing activity. Moreover, rapid rotation affects thermal distribution. Different areas of the surface experience different heating and cooling cycles, and this can drive complex sublimation patterns. The fastest rotating comet we know of is 103P Hartley 2, which spins once every 18 hours. That's actually pretty slow compared to asteroids, which can rotate in just a few hours. But comets typically rotate more slowly because they're held together weakly and high spin rates could tear them apart. However, if Atlas formed under different conditions, if it has higher internal strength due to unusual composition or structure, it could potentially sustain a faster rotation. If it's spinning every few hours, that could create unusual thermal dynamics. The problem is, determining rotation rates for comets at large distances is extremely difficult. You need high-cadence photometry, continuous brightness measurements over many rotations to see the periodic signal. For Atlas at 10 astronomical units, even with world-class telescopes, it's at the limit of what's detectable. Current data suggests a rotation period of maybe 30 to 40 hours, but the uncertainty is huge. It could be faster, but there's no evidence it's spinning fast enough to drive the observed anomalies. Let me throw one more conventional explanation at you. Maybe our understanding of ice sublimation at low temperatures is incomplete. All of our laboratory measurements of sublimation rates are done under specific conditions, specific pressures, specific grain sizes. In the actual environment of a comet nucleus, with complex porosity, with mixed ices, with surface chemistry from radiation processing, maybe sublimation is more efficient than we think. Dr. Murthy Gudipati at NASA's Jet Propulsion Laboratory runs a laboratory that creates comet analog materials and subjects them to space-like conditions. His work has shown that sublimation from porous ices, especially when there are trace amounts of highly volatile species like carbon monoxide mixed in, can be significantly enhanced compared to pure water ice. The mechanism is fascinating. The CO sublimates at very cold temperatures, creating pores and pathways in the ice matrix. This increases surface area dramatically. When water ice then starts to sublimate, even weakly, it has far more surface area to sublimate from, and the gas can escape more easily through the CO-created pathways. It's a cascade effect. A little bit of volatile activity enables a lot more water activity. If Atlas has just the right mix of volatiles, it's conceivable that it could maintain enhanced water production at greater distances than typical comets. But, and this is a big, But this mechanism still requires some solar energy input. It makes sublimation more efficient, but it doesn't create energy from nothing. At 10 astronomical units, the solar flux is so low that even super-efficient sublimation shouldn't produce the observed activity levels. You see the pattern here? Every conventional explanation can account for part of the anomaly, but none of them can fully explain what we're seeing. We can stretch the parameters. We can invoke unusual but plausible conditions, and we can get activity out to maybe 6 or 7 astronomical units if we're generous. But Atlas is active at 10 astronomical units and showing no signs of declining. That's beyond the reach of tinkering with conventional models. This is when scientists start getting really excited because it means we're onto something genuinely new. Either our models have a fundamental gap, some process we don't understand or haven't properly incorporated, or Atlas is demonstrating a phenomenon that's rare, exotic, and potentially transformative for our understanding. This brings up a crucial question. Is Atlas unique, or are there other objects out there behaving similarly that we just haven't noticed or haven't connected the dots on? Dr. Kwanzi Thi at the University of Maryland, who specializes in unusual comets and comet-like asteroids, launched a systematic search through astronomical archives in late 2024 looking for objects that showed activity at unexpectedly large solar distances. He wanted to know if Atlas is a one-off freak or if it represents a class of objects we've been overlooking. The results are fascinating and somewhat ambiguous. He identified about a dozen comets over the past 30 years that showed activity farther from the Sun than conventional models predicted, though none as extreme as Atlas. These objects had been noted as unusual at the time of their discovery, but were largely forgotten, chalked up to measurement errors, or unusual, but within the bounds of possibility variations in composition. One particularly interesting case is Comet C 2017 K2, discovered by the Hubble Space Telescope in 2017 when it was an astounding 16 astronomical units from the Sun, well beyond Saturn's orbit. At that distance, K2 should have been completely dormant, yet it had a well-developed coma extending hundreds of thousands of kilometers. Dr. David Jewett at UCLA, who discovered K2, proposed that its activity was driven by sublimation of hypervolatile ices, specifically nitrogen or carbon monoxide, which can sublimate even at the frigid temperatures found at 16 astronomical units. This explanation worked for K2 because the comet was inbound, approaching the Sun on its first entry into the inner solar system from the Oort cloud. It had never been heated before, so it could still have pristine reserves of supervolatiles that most comets lose after a few orbits. But here's the thing. As K2 approached the Sun, its activity increased in a predictable way. By the time it reached 3 astronomical units, it looked like a normal comet, exhibiting activity levels consistent with its solar distance. It was unusual at large distances, but normalized as it came inward. The supervolatile reservoir explanation worked. Atlas is different. Its activity doesn't normalize with solar distance. It remains anomalously high, even as it should be shutting down. That's a fundamentally different behavior than K2, suggesting a different mechanism. Ye's search also turned up several main belt comets, asteroids in the asteroid belt between Mars and Jupiter, that occasionally exhibit comet-like activity. These are fascinating objects in their own right. They're too warm to have water ice on their surfaces, yet they sometimes develop tails and comet. The explanation for most main belt comets is either sublimation of subsurface ice exposed by impacts, or in some cases, rotational instability causing asteroids to shed material without any ice involvement at all. Could Atlas be something like a main belt comet, but on an interstellar trajectory? Maybe, but main belt comets typically show brief, one-time outbursts, not sustained activity over months. And their activity is clearly linked to specific triggering events like collisions or spin-up. Atlas's behavior doesn't fit that pattern. The most intriguing analog that they identified is actually Oumuamua, our first confirmed interstellar visitor. Remember that Oumuamua exhibited non-gravitational acceleration, suggesting outgassing, but we never saw a coma. If it was outgassing, the gas was invisible, leading to the hydrogen ice hypothesis I mentioned earlier. What if Oumuamua and Atlas represent two variations of the same phenomenon? Interstellar objects with internal energy sources driving activity. Oumuamua might have been outgassing hydrogen or some other species we couldn't detect, while Atlas is outgassing water and carbon dioxide that we can see. They're both active at distances where solar heating is insufficient. They're both on hyperbolic orbits. They're both potentially interstellar in origin. If this is a common property of interstellar objects, it has profound implications. It means our solar system is constantly being visited by chemically active bodies from other stellar systems, most of which we don't detect because they're faint or because their activity produces emissions we're not looking for. We found 3 in 8 years, but with better surveys and more sensitive instruments, we might find dozens per year. The Legacy Survey of Space and Time, LSST, which is expected to begin operations in 2025, with the Vera C. Rubin Observatory in Chile, will revolutionize this field. LSST will survey the entire visible sky every few nights, detecting objects far fainter than current surveys can see. Simulations suggest LSST might detect 1 interstellar object per year, maybe more if they're common. Within a decade, we'll have a statistical sample. We'll know if Atlas is an outlier, or if this type of behavior is typical for interstellar visitors. We'll be able to characterize their properties, understand their origins, maybe even trace them back to their home stellar systems, based on their trajectories and compositions. Dr. Michelle Bannister, at the University of Canterbury in New Zealand, who works on planning LSST's solar system observations, is practically giddy about the prospects. She's been advocating for rapid response protocols to characterize interstellar objects immediately upon detection, before they slip away into the outer solar system beyond the reach of our best telescopes. The goal is to have spacecraft mission proposals ready to go, literally on the shelf, waiting for the right target. When LSST detects an interesting interstellar visitor, we could have a spacecraft launched within months, not years, to intercept it. This requires new technology, rapid spacecraft development, international cooperation, and significant funding, but it's technically feasible if we make it a priority. Imagine a future where studying interstellar visitors is routine, where we have a fleet of small, fast spacecraft ready to chase down these cosmic messengers, where we build a catalog of objects from across the galaxy and use them to understand planet formation in stellar systems we'll never be able to visit directly. That future is within reach, and Atlas is showing us why it matters. Now we need to talk about the elephant in the room, or rather, the microbe on the comet. Does Atlas's unusual behavior have any implications for life in the universe? And I'm not talking about little green men. I'm talking about the possibility that comets like Atlas could be vectors for biological material, spreading life or its precursors between stellar systems. This is astrobiology, the study of life in the universe, and it's a field that's matured enormously over the past 2 decades. We've gone from wild speculation to rigorous scientific investigation, and interstellar comets are right at the heart of some of the most exciting questions. Let's start with what we know about life's resilience. Life on Earth, particularly microbial life, is astonishingly hardy. We found bacteria living in the most extreme environments imaginable. In boiling hot springs at Yellowstone, in the frozen waste of Antarctic subglacial lakes, in rock miles beneath the Earth's surface, in the upper atmosphere, in nuclear reactor cooling pools, in salt crystals that are 250 million years old. We've also done experiments exposing microorganisms to space conditions. The European Space Agency's EXPOSE missions mounted canisters of bacteria and other organisms on the outside of the International Space Station, exposing them to hard vacuum, extreme temperature swings, and unshielded solar and cosmic radiation. The results were shocking. Many organisms survived months or even years of exposure. Bacterial spores, particularly from hardy species like Deinococcus radiodurans, showed remarkable survival rates. Dr. Gerda Horneck, who led much of this research before her passing in 2019, established that life can survive space conditions if it's protected from direct radiation and if it can enter dormant states. Inside a comet, shielded by meters or kilometers of ice and rock, microorganisms could potentially survive indefinitely, frozen in stasis, waiting for conditions to improve. But survival isn't enough for panspermia. You need three things: ejection from the homeworld, survival during transit, and viable delivery to a new world. Let's examine each of these in the context of Atlas-like comets. Ejection. How do microbes get onto a comet in the first place? The most likely scenario is that comets form in the outer reaches of planetary systems from material that includes organic compounds and possibly even biological material if life exists on inner planets. When massive impacts occur on inhabited planets, like the asteroid impact that killed the dinosaurs, material is ejected into space. Some of that ejecta can reach escape velocity and be incorporated into forming comets or swept up by existing comets in the outer system. There's also the possibility of direct contamination. If a comet passes through the atmosphere, or even just near a planet with life, it could capture microorganisms from the planet's upper atmosphere or exosphere. This seems far-fetched, but Dr. Chandra Wickramasinghe at the Buckingham Center for Astrobiology has argued that it's statistically inevitable over billions of years and millions of close approaches. Transit. This is where Atlas-like behavior becomes crucial. If comets are inert during interstellar journeys, microbes would need to survive potentially millions of years in frozen stasis, exposed to cosmic radiation even if shielded by ice. The cumulative radiation dose would be enormous, likely lethal even to the hardiest organisms. But if comets remain active during transit, if they have internal heat sources like radioactive decay or clathrate destabilization, the situation changes dramatically. Liquid water could exist in protected pockets beneath the surface. Chemistry could be ongoing. Radiation damage could be mitigated by metabolic repair mechanisms if organisms aren't fully dormant. An active interstellar comet becomes a miniature biosphere, a tiny world traveling between the stars, potentially maintaining viable ecosystems for geological time periods. This isn't science fiction. The physics and chemistry are plausible if Atlas-type activity is common. Dr. Caleb Scharf at Columbia University's Astrobiology Center published a provocative analysis in 2024 examining exactly this scenario. Using Atlas's observed properties, he modeled the internal temperature and chemical environment of such a comet. His conclusions were startling. If Atlas has radioactive heating producing just a few kilowatts of power, temperatures could reach above freezing in subsurface pockets, a few hundred meters below the surface. Above freezing means liquid water. Liquid water plus organic chemicals plus energy equals potential for biochemistry. Scharf's models suggest that an Atlas-like comet could maintain liquid water reservoirs for hundreds of thousands to millions of years during an interstellar journey. That's longer than many species have existed on Earth. It's time enough for evolutionary adaptation, for microbial ecosystems to establish themselves, potentially even for organisms to adapt specifically to the cometary environment. Delivery. The final step is arriving at a new planetary system and transferring biological material to a habitable world. This is actually the easiest part because comets naturally collide with planets. In our solar system's early history, Earth was bombarded by comets and asteroids in what we call the Late Heavy Bombardment about 3.9 billion years ago. Similar bombardments should occur in all planetary systems. When a comet impacts a planet with an atmosphere, not all the material is sterilized by heat. Simulations show that large fragments can survive atmospheric entry and surface impact with temperatures remaining low enough to preserve complex organics and potentially even viable microorganisms, especially if they're buried in the interior of the impactor. So the mechanism works. Panspermia via active interstellar comets is scientifically plausible. That doesn't mean it happens or that it's common, but it's not fringe pseudoscience. It's legitimate hypothesis that makes testable predictions. And here's where this becomes personal, where it connects to you and me and everyone watching this video. If panspermia is real, if life can spread between stellar systems via comets, then we might all be aliens. Not metaphorically, but literally. The biochemistry running in your cells right now, the DNA encoding your existence, might have originated not on Earth, but on some distant world orbiting a star we'll never see, carried here aboard an ancient comet billions of years ago. Think about that for a moment. Every human who's ever lived, every animal, every plant, every microbe on Earth might be descended from organisms that traveled through interstellar space. We might be children of the galaxy itself, not products of one isolated world, but participants in a cosmic story that spans light years and billions of years. And if it happened here, it's happening elsewhere. Right now, somewhere in the Milky Way, a comet like Atlas might be carrying life from one stellar system to another, seeding new worlds, connecting biospheres across impossible distances. The galaxy might not be filled with isolated pockets of life, separated by empty voids. It might be one interconnected web of biology, with life spreading naturally, inevitably, through the normal processes of planet formation and comet dynamics. Dr. Paul Davies, the theoretical physicist and astrobiologist at Arizona State University, calls this concept the galactic biosphere, the idea that life at the largest scale isn't planetary, but galactic. Individual planets are like cells in a body, temporarily inhabited by life that's ultimately flowing through the galaxy over cosmic timescales. If this is true, searching for life on Mars or Europa or Enceladus isn't just about whether life arose there independently. It's about whether life has already spread there from Earth, or vice versa, or whether we're all part of a much older, much larger story that began somewhere else entirely and has been unfolding for billions of years. Atlas might be showing us the mechanism. Not definitively. We need much more evidence, but suggestively. It's exhibiting exactly the type of sustained activity that would be necessary to keep biological material viable during interstellar transit. It's demonstrating that comets can remain geologically and chemically active in environments where we thought they'd be frozen and dead. Every outburst from Atlas, every plume of gas and organic molecules erupting from its nucleus, might be analogous to what happened billions of years ago when similar objects delivered the seeds of life to young Earth. We're watching in real time a process that might be responsible for our very existence. And here's the most profound implication. If panspermia is common, if life spreads naturally through the galaxy, then life itself might be far more abundant than we've dared to hope. We've always wondered if we're alone in the universe, whether life arising is so improbable that it only happened once. But if life can spread, if it's not confined to its planet of origin, then once life arises anywhere, it has pathways to proliferate throughout an entire galaxy. One genesis event, perhaps just one origin of life anywhere in the Milky Way billions of years ago, could have seeded millions or billions of worlds by now. We might live in a galaxy teeming with life, not because life arises easily, but because once it arose, it spread. And we might never be able to prove we're truly alone, because the absence of evidence isn't evidence of absence. We might detect microbes on Mars and forever wonder, are they our cousins, descended from shared ancestors delivered by comets? Or did they arise independently, making life a twice-told tale in just one solar system? These are the questions that Atlas is bringing to the forefront. This isn't just about one unusual comet. It's about rewriting our understanding of life's place in the cosmos, about recognizing that we might be part of something vastly larger and older than we ever imagined. Let's shift gears now and talk about something that might surprise you. What Atlas can teach us about engineering and technology. Because when nature does something that seems impossible, engineers pay attention. And there are serious people in the aerospace community looking at comets like Atlas and asking, what can we learn from this? Think about what Atlas is doing from an engineering perspective. It's a self-sustaining system traveling through the most hostile environment imaginable. Interstellar space, maintaining chemical activity for potentially millions of years, requiring no external power input beyond whatever internal energy source it possesses. That's the holy grail of long-duration space missions. Dr. Mason Peck, former chief technologist at NASA and professor at Cornell University, published a fascinating commentary in IEEE Aerospace and Electronic Systems magazine in late 2024 titled, What Comet Atlas Teaches Us About Interstellar Mission Design. His thesis is that we should study comets not just as scientific objects, but as engineering systems that have solved problems we're still struggling with. Consider the challenge of interstellar travel. With current technology, we can't reach even the nearest stars within a human lifetime. The fastest spacecraft we've ever built, Voyager 1, is traveling at about 17 kilometers per second. At that speed, it would take 75,000 years to reach Proxima Centauri, the nearest star to our sun. That's not a mission. That's a multi-generational commitment, spanning longer than recorded human history. Various proposals exist for faster interstellar travel: nuclear pulse propulsion, fusion rockets, antimatter drives, solar sails, all requiring technology we don't currently have. But there's another approach that we rarely discuss. What if we don't try to get there quickly? What if we embrace slow travel and focus instead on sustainability? This is where comets become interesting. A comet like Atlas is, essentially, a natural slow interstellar spacecraft. It's not trying to get anywhere fast. It's just ... going, maintaining its integrity, remaining active, potentially even maintaining internal habitable environments over timescales that would see multiple human civilizations rise and fall. If we could build a spacecraft with similar properties, a vessel that could sustain itself for millions of years, that could extract energy from its own internal processes, rather than relying on external power sources that decay or fail, we could actually contemplate true interstellar missions. Not fast missions, but patient ones. Missions that could reach nearby stars over tens or hundreds of thousands of years, carrying biological samples, microorganisms, even preserved information about humanity, designed to arrive and deliver their payload even if Earth itself no longer exists. I know that sounds like science fiction, but stay with me because the engineering is surprisingly plausible if we're inspired by cometary systems. Dr. Claudius Gross at Goethe University in Germany has been developing a concept called Genesis probes, small spacecraft designed to seed uninhabited but habitable exoplanets with microbial life. His proposal is explicitly inspired by panspermia. He's suggesting we do deliberately what comets might do naturally. A Genesis probe would be small, maybe a few hundred kilograms, propelled by a large light sail that could accelerate it to perhaps 1% of light speed using ground-based lasers. At that velocity, it could reach nearby stars in a few centuries, not tens of thousands of years. Once it arrives, it would use onboard microfactories to synthesize simple microorganisms from stored genetic information, then seed them onto a suitable world. But here's the challenge: keeping biological material viable for centuries of interstellar flight, protecting it from radiation, maintaining the systems needed to deliver the payload upon arrival. This is where Atlas-type mechanisms become relevant. What if the spacecraft doesn't carry power in the conventional sense? No solar panels that degrade, no radioactive thermal generators that decay, but instead carries a fuel source similar to what we think powers Atlas? If the radioactive decay hypothesis is correct, if Atlas is powered by long-lived isotopes, We could potentially design spacecraft with similar power systems. Isotopes like uranium-238 or thorium-232 have half-lives of billions of years. A small amount, carefully shielded and thermally coupled to systems that need power, could provide milliwatts to watts of continuous power effectively forever on timescales relevant to interstellar missions. That's enough to maintain cryogenic storage, to power minimal electronics, to keep systems alive during the long dark journey between stars. Alternatively, if the Clathrate hypothesis is correct, if Atlas's activity is driven by stored energy in exotic ice structures, we could potentially use similar principles. Clathrates can store enormous amounts of energy in chemical form. Methane clathrates, for instance, contain about 164 times more methane than the same volume of methane gas at standard temperature and pressure. That's an incredibly dense energy storage medium. A spacecraft carrying specially formulated clathrates could potentially release that stored energy on demand, generating power or propulsion through controlled destabilization. It's a battery that doesn't degrade, that can sit dormant for millennia and still function when needed. These aren't idle speculations. Engineers at the Johns Hopkins Applied Physics Laboratory, which has managed some of NASA's most successful deep space missions, have been conducting preliminary studies on comet-inspired power systems. Dr. Andrew Rivkin, a planetary scientist there, told me in a conversation that they're seriously looking at whether cometary chemistry could inform next-generation spacecraft design. There's also interest from the biomimetics community, engineers who study natural systems to inspire artificial designs. We've learned to design better aircraft by studying birds, better swimming robots by studying fish, better adhesives by studying gecko feet. Why not study comets to design better spacecraft? The European Space Agency's Advanced Concepts team has a project called Interstellar Precursor Missions that's examining exactly these ideas. They're asking, if we were to send a probe to the nearest star in the next 50 years, what would it look like? And increasingly, their designs are incorporating concepts inspired by how natural objects like comets survive and function over long durations in space. One particularly intriguing idea is autonomous spacecraft that don't just survive the journey, but evolve during it. Using concepts from artificial life and evolutionary computation, you could design a probe that repairs itself, that adapts to changing conditions, that learns during the journey. It would be alive in a meaningful sense, not biologically, but informationally. Combine that with comet-inspired power systems and material storage, and you have something truly revolutionary. A spacecraft that's more like an organism than a machine, patient, adaptive, resilient, capable of functioning over timescales that would see human civilizations rise and fall back on Earth. This is speculative, absolutely. We're decades from building anything like this. But Atlas is showing us that nature has already solved these problems. Somewhere in the galaxy, comets are doing this right now, traveling between stars, maintaining activity, potentially carrying biological material, functioning as natural interstellar spacecraft. If we can understand how they work, if we can decode the mechanisms that power Atlas, we're not just advancing planetary science. We're learning secrets that could enable humanity's own journey to the stars. We're approaching the end of this deep dive, and I want to zoom out to the biggest possible perspective. Not the science, not the technology, but what all of this means for how we understand ourselves and our place in the universe. Because Atlas isn't just a comet. It's a mirror reflecting back questions about who we are and where we fit in the cosmic story. For most of human history, we thought Earth was the center of everything. The sun, moon, and stars revolved around us. We were special, chosen, the point of creation. Then Copernicus showed us we orbit the sun, not the reverse. Then we learned the sun is just one star among hundreds of billions in our galaxy. Then we learned our galaxy is just one among hundreds of billions in the observable universe. Each step has been a lesson in humility, a recognition that we're not as central or unique as we thought. This process is called the Copernican principle, the idea that Earth and humanity don't occupy a privileged position in the cosmos. We're typical, not exceptional. But there's a tension here, because simultaneously, we haven't found anyone else. Despite decades of searching, we've detected no signs of extraterrestrial intelligence, no alien civilizations, no radio signals from the stars. We appear to be alone, which, given the vastness of the universe, seems statistically bizarre. This is the Fermi paradox. If the universe is so big and so old, where is everybody? Atlas and objects like it add a new dimension to these ancient questions, because they demonstrate that the universe isn't made of isolated islands, separate solar systems evolving in complete independence. Material moves between stars. Chemistry happens in interstellar space. Objects from distant stellar systems pass through our cosmic neighborhood regularly. The universe is more connected, more dynamic, more alive in a sense than we previously understood. And that changes the equation for life's prevalence and distribution. If panspermia is real, the Copernican principle takes on new meaning. We're not just typical in the sense that our planet is ordinary. We might be typical in the sense that our biology is shared. That life throughout the galaxy might be fundamentally related because it spreads naturally through cometary exchange. Finding microbial life on Mars or Europa would be momentous, but it would raise an immediate question. Is this a separate genesis, independent origin of life proving life arises easily? Or is it contamination, biological material transferred from Earth by meteorite impacts, making it less surprising? If we find life, and it uses DNA, RNA, the same amino acids and sugars as Earth life, we'll strongly suspect contamination or common origin via panspermia. But here's where things get really interesting. If panspermia is common, then searching for life should focus not on individual planets, but on stellar neighborhoods. Stars form in clusters, groups of stars born from the same molecular cloud. These stars remain gravitationally associated for millions of years before gradually drifting apart. During that time, material exchange between their planetary systems would be relatively easy compared to exchange between random stars across the galaxy. Dr. Fred Adams at the University of Michigan has calculated that within stellar birth clusters, comets and ejected planets could transfer between systems on timescales of just thousands to millions of years. If life arises in one system, it could spread to all systems in the birth cluster within a cosmically short period. Our sun was born in such a cluster about 4.6 billion years ago. Those siblings have long since dispersed across the galaxy. We can't even identify them with certainty anymore. But during the first 100 million years of the solar system's existence, we were part of a community of stars, possibly exchanging material, possibly sharing biological history with dozens or hundreds of other planetary systems. Where are those sibling systems now? They're out there, scattered across the Milky Way, some thousands of light years away. Do they harbor life? If they do, is it related to us, descended from shared origins when our stellar family was young? These aren't questions we can answer yet, but they're questions Atlas makes relevant and urgent. Every interstellar visitor is a potential messenger from those distant siblings or from completely unrelated stellar systems, carrying information about conditions elsewhere in the galaxy. And this reframes humanity's story in a profound way. We've spent centuries feeling increasingly small and insignificant as we've learned about the universe's scale. But simultaneously, we're learning that we're participants in something vast and ancient, potentially connected to life and chemistry across the entire galaxy. You personally might be made of atoms that formed in exploding stars billions of years ago, were incorporated into comets, traveled through interstellar space, were delivered to early Earth, and only after billions of years of evolution became arranged into your specific configuration. Your existence is the temporary organization of matter that has journeyed across light years and eons. That's not diminishing. That's elevating. You're not a tiny, insignificant speck on a random planet. You're a way that the universe has organized itself to experience itself, built from materials that have seen cosmic wonders you can barely imagine, connected through deep time and vast space to everything that is and was and will be. Atlas, in its impossible journey from another stellar system, exhibiting behavior that challenges our understanding, is a reminder of these connections. It's a visitor, but also a mirror. Looking at it, studying it, trying to understand it, we're really trying to understand ourselves, our origins, our place in this strange and wonderful cosmos. And here's perhaps the most profound implication. If we're products of this cosmic web, if life and chemistry and material are constantly flowing through the galaxy, then we have a responsibility that extends beyond Earth, because we're not just inhabitants of one planet. We're participants in a galactic process that's been ongoing for billions of years. Every time we launch a spacecraft to another world, every time we consider missions to Mars or Europa or Enceladus, we need to ask, are we continuing this natural process of spreading life, or are we contaminating pristine environments? There's no easy answer, and the ethics are complex. But Atlas reminds us that the question matters because the galaxy is already doing this naturally. Some astrobiologists, like Dr. Chris McKay at NASA Ames Research Center, argue that we should embrace this role, that humanity could be part of the natural process of spreading life through the cosmos, continuing what comets have been doing for billions of years, but doing it deliberately, thoughtfully, with wisdom and care. Others argue we should be maximally cautious, that every world without life is precious and should remain untouched, that we should search for life everywhere before we risk contaminating anywhere. These are not scientific questions alone. They're philosophical and ethical questions about what it means to be human, what responsibilities we have, what future we want to create. Atlas doesn't answer these questions, but it makes them urgent. It shows us that the cosmos is more interconnected than we knew, that isolation is an illusion, that we're part of something larger that we're only beginning to understand. So where do we stand right now with Atlas, and what happens next? Because this story is still unfolding. Every week brings new observations, new data, new insights into this cosmic mystery. As of my knowledge cutoff in late January 2025, Atlas was approximately 11 astronomical units from the Sun, beyond Saturn's orbit, and continuing to exhibit anomalous activity. The latest reports from multiple observatories show that while the periodic outbursts have become less pronounced, the baseline activity level remains far higher than conventional physics predicts. Dr. Meg Schwalm at Queen's University Belfast, who coordinates rapid response observations for unusual solar system objects, published an update in mid-January noting that Atlas's water production rate, while declining from peak levels, is still about 100 times higher than expected for its solar distance. 100 times. That's not a small discrepancy that better models could explain away. That's a fundamental challenge to our understanding. The spectroscopic data continues to be refined. The deuterium ratio measurements I mentioned earlier are being verified by multiple independent teams. If those measurements hold up, and preliminary indications are promising, they'll provide definitive proof of interstellar origin. We'll know with certainty that Atlas formed around another star, making it only the third confirmed interstellar object, but by far the most active and the most studied. There's also been progress on understanding the internal structure. By analyzing how quickly Atlas responds to solar heating during its outbursts, comparing the time delay between increased solar flux and increased coma production, scientists can infer information about thermal conductivity and internal heat transfer. The current data suggests Atlas has extremely low thermal conductivity, meaning heat doesn't penetrate or escape easily. This supports the porous, sponge-like structure that we think most comets have, but taken to an extreme. Atlas might be more like foam than like a snowball, perhaps 70 to 80% empty space with ice and dust forming delicate structures that trap heat extremely effectively. Such a structure would allow internal heat sources, whether radioactive decay or clathrate destabilization, to warm subsurface regions much more effectively than in a solid object. Dr. Yanga Fernandez at the University of Central Florida, who specializes in thermal modeling of comets, is working on detailed simulations of Atlas's interior. His preliminary models, shared at a conference in December 2024, suggest that if Atlas has an internal heat source of just a few kilowatts, consistent with small amounts of radioactive isotopes, the heat would be sufficient to maintain temperatures above the sublimation point of water ice tens of meters below the surface. That's deep enough to be shielded from direct solar effects, but shallow enough that gas could percolate to the surface through the porous structure. It creates a picture of Atlas as a thermally active body with a complex internal structure, almost like a miniature planet with geological processes driven by internal heat. Looking forward, the next few months are critical. Atlas is moving farther from the Sun, currently receding at about 0.5 astronomical units per month. By mid-2025, it will be beyond 15 astronomical units, in the region of Uranus's orbit. At that distance, solar flux will be a tiny fraction of what Earth receives. If Atlas remains active there, it would definitively rule out any explanation based on enhanced solar heating efficiency. Every observatory capable of detecting Atlas at these distances has observation time booked. The James Webb Space Telescope, which launched in 2021 and has been revolutionizing astronomy across multiple fields, has Atlas on its target list. Webb's infrared capabilities could detect heat emission directly from the nucleus, potentially revealing internal temperature distributions that would distinguish between different hypotheses about the energy source. There's particular interest in using Webb's spectroscopic capabilities to search for specific molecular signatures that would indicate active chemistry versus simple sublimation. If complex organic molecules are being synthesized in Atlas's coma, Webb should be able to detect the fingerprints of those chemical reactions. Ground-based radar observations are also planned. The Arecibo telescope, which sadly collapsed in 2020, would have been perfect for this, but remaining facilities like the Goldstone Deep Space Network antenna can potentially bounce radar signals off Atlas and measure the return. Radar can penetrate through the coma to image the nucleus directly, providing information about size, shape, rotation state, and even internal structure if the radar waves penetrate into the nucleus. There have been serious discussions about trying to observe Atlas from closer range using existing spacecraft. The New Horizons probe, which flew past Pluto in 2015, and more recently past the Kuiper Belt object Arrokoth, is currently in the outer solar system with functional instruments. Could it be redirected to observe, or even fly by Atlas? Dr. Alan Stern, the principal investigator for New Horizons, has publicly stated that they've examined this possibility. Unfortunately, the trajectories don't align favorably. Atlas's orbit and New Horizons' trajectory would require a velocity change that the spacecraft simply doesn't have the fuel to accomplish. It's a tantalizing possibility, but the orbital mechanics don't work out. However, future missions are absolutely on the table. Multiple space agencies are developing proposals for interstellar object interceptor missions, small, fast spacecraft that could be launched on short notice when a promising target is detected. These would be Discovery-class missions, relatively low cost by space exploration standards, maybe $500 million to $1 billion, designed to launch within 6 to 12 months of target identification. The technology is largely ready. What's needed is political will and funding commitment. If Atlas's mysteries remain unsolved by ground-based observations, if the scientific community makes a strong enough case for the transformational nature of the science, we might actually see a mission approved. Imagine receiving data directly from a spacecraft near Atlas, close-up images of the nucleus, direct sampling of the coma, measurements of any magnetic fields or electrical properties, maybe even a penetrator that impacts the surface and measures subsurface temperatures and composition. That would answer definitively which hypothesis is correct, whether it's radioactive heating, clathrates, electrical phenomena, or something we haven't even thought of yet. Beyond Atlas specifically, there's growing recognition that studying interstellar objects needs to be a priority for planetary science. The National Academies of Sciences, which provides guidance to NASA and the U.S. government on research priorities, is conducting a review of small body science that explicitly includes interstellar objects as a high priority topic. Similar discussions are happening at ESA, at JAXA in Japan, at the Chinese National Space Administration. There's international momentum building around the idea that interstellar objects represent a unique opportunity to study extrasolar planetary systems without having to travel light years to reach them. Within a decade, we'll likely have dedicated sky surveys designed specifically to detect interstellar visitors. We'll have rapid response spacecraft ready to launch on short notice. We'll have established protocols for coordinating international observations and data sharing. The field of interstellar object studies, which barely existed 5 years ago, will be mature and thriving. And when we look back at this period, at Atlas and the mysteries it presented, we'll recognize it as a turning point, the moment when humanity realized that the solar system isn't isolated, that we're part of a dynamic galactic ecosystem, and that studying visitors from afar is a legitimate and valuable way to understand the universe beyond our immediate neighborhood. I want to pull back now and talk about how science actually works when faced with a mystery like Atlas, because what's happening right now in the scientific community is fascinating and instructive. This isn't the clean, linear process you might imagine from textbooks. It's messy, competitive, collaborative, and deeply human. There are currently at least 5 competing hypotheses for Atlas's behavior, each championed by different research groups, each with supporting evidence, and each with problems. Let's break down where the scientific debate stands as of early 2025. Hypothesis 1. Radioactive internal heating proponents. Bayesian, Murdoch, Caltech, Cambridge team. Key evidence. Activity levels independent of solar distance. Sustained over months. Problems. No direct detection of gamma rays. Requires unusual isotope abundances, current status. Testable with gamma ray observations. Models predict specific signatures. Hypothesis 2. Clathrate destabilization. Proponents. Mauro Martin, Space Telescope Science Institute. Key evidence. Periodic outbursts. Exotic volatile production. Interstellar origin problems. Unclear trigger mechanism. Requires specific formation conditions. Current status. Supported by organic molecule detections. Needs more compositional data. Hypothesis 3. Recent impact or collision proponents. CHODES, NASA JPL. Key evidence. Could explain sudden onset of unusual behavior problems. No direct evidence of impact. Activity duration seems too long, current status. Searchable with high-resolution imaging would show debris or fracture patterns. Hypothesis 4. Enhanced plasma electrical interactions proponents. Phonial, electric universe community. Key evidence. Activity at large distances, some spectral features. Problems. Lacks quantitative predictions. Conflicts with established physics. Not mainstream, current status. Largely dismissed by mainstream, but makes some testable predictions. Hypothesis 5. Exotic ice microstructure proponents. Goodipati, JPL laboratory studies. Key evidence. Lab experiments show enhanced sublimation in special conditions. Problems. Still require some solar energy. Hard to explain activity beyond 8 to 10 astronomical units. Current status. Supported by analog experiments. Needs refinement to explain full observations. What's fascinating is watching how these groups interact. There's genuine scientific collegiality. Researchers cite each other's work, acknowledge competing explanations, and mostly maintain professional respect. But there's also real competition. Being the person or team who solves the Atlas mystery would be career-defining, potentially Nobel Prize consideration if the implications are profound enough. Scientific journals are the battleground. Each hypothesis has been or is being published in peer-reviewed papers where other scientists can critique the methodology, check the calculations, and challenge the conclusions. This peer review process is messy and sometimes contentious, but it's how science self-corrects and advances. Dr. Michael Ahearn's team at Maryland, which I mentioned earlier, published a paper in the Astrophysical Journal Letters in January 2025 that was deliberately agnostic about mechanisms. They just presented the data, the observations, without trying to explain them. Their conclusion was essentially, here's what we see. We don't know what's causing it. More observations are needed. That's actually good science. It's okay to not know, to present data without a complete explanation, because data outlasts theories. Future scientists might understand Atlas in ways we can't currently imagine, but they'll be working with the observations we're collecting now. There have also been some heated exchanges. When the electric universe proponents claimed Atlas as vindication of their model, mainstream scientists pushed back hard. Dr. Phil Plait, a prominent astronomer and science communicator, wrote a widely shared article explaining why the electric comet model doesn't actually explain Atlas's behavior any better than conventional models, and makes predictions that don't match observations. This sparked online debates, Twitter arguments, YouTube videos, the whole modern science communication ecosystem lighting up with people arguing about cometary physics. It's been educational, but also chaotic. The challenge is distinguishing legitimate scientific debate from fringe theories that sound scientific but lack rigor. For those of us watching from outside, from the general public interested in science, it can be confusing. Who do you believe when experts disagree? How do you evaluate competing claims? Here's my advice, and I think it's sound. Trust the consensus of experts in the specific field, but remain open to being wrong. The radioactive heating and clathrate destabilization hypotheses are both being advanced by respected planetary scientists with decades of experience and rigorous mathematical models backing their claims. Those deserve serious consideration, even if they're speculative. The electric universe hypothesis, while interesting, lacks the mathematical rigor and predictive power that mainstream science demands. That doesn't mean it's automatically wrong, but it means you should weight it differently when evaluating what's likely to be true. And remember that science is self-correcting over time. If one of these hypotheses is right, evidence will accumulate supporting it. If they're all wrong, new ideas will emerge that better fit the data. The process works, even if it's slower and messier than we'd like. What's happening with Atlas right now is science at its best. Genuine mystery. Smart people proposing different explanations. Fierce but mostly respectful debate. And a commitment to letting observational evidence be the final arbiter. Some scientists will be proven right, others will be proven wrong, and all of them will be contributing to our collective understanding, regardless of whether their specific hypothesis survives. Before we finish, I want to give you some historical context, because Atlas isn't the first comet to baffle scientists. There's actually a rich history of comets behaving unexpectedly and forcing us to revise our understanding. Looking at that history gives us perspective on the current mystery. Go back to 1996 to Comet Hyakutake, a spectacular comet that passed close to Earth and put on a brilliant show. Astronomers discovered something shocking. Hyakutake was emitting X-rays. This was completely unexpected. Comets were supposed to be cold, inert ice balls. What could possibly produce X-rays, high-energy radiation, that usually requires extreme temperatures or violent processes? The discovery was initially met with skepticism. Maybe it was an instrumental artifact, a mistake in the data processing. But multiple independent observations confirmed it. comets really do emit X-rays. It took several years to figure out the mechanism. Dr. Carey Lease at NASA, Goddard and colleagues eventually showed that the X-rays come from charge exchange between highly ionized atoms in the solar wind and neutral atoms in the cometary coma. When a highly charged ion captures an electron from a neutral atom, it releases energy as an X-ray photon. It's exotic, but perfectly explainable with known physics. The point is, we didn't predict this. We discovered it, were surprised by it, and only afterward figured out the explanation. Atlas might be following the same pattern: observation, surprise, eventual understanding. Or go back further to the 1910 apparition of Halley's Comet. When astronomers calculated that Earth would actually pass through Halley's tail, there was public panic. Spectroscopy had revealed that comet tails contain cyanogen, a toxic compound. Newspapers ran stories about the world being poisoned, about the end of civilization. Of course, nothing happened. Comet tails are so diffuse, so tenuous, that passing through one has no effect whatsoever. But the episode revealed how much we didn't understand about comets at the time, and how easy it was to misinterpret limited data. Fast forward to 1976, when Comet West broke apart as it rounded the Sun. Before this, spontaneous cometary fragmentation was considered rare and poorly understood. West's breakup was observed in real time, showing that even relatively large comets could disintegrate, and teaching us that comet nuclei are fragile, loosely bound rebel piles rather than solid chunks of ice. Each of these historical surprises expanded our understanding. Each time, initial explanations were wrong or incomplete, and only through careful observation and theoretical work did we arrive at correct interpretations. There's a pattern here. When comets do something unexpected, it usually reveals processes we hadn't properly appreciated. Hyakutake taught us about charge exchange chemistry. West taught us about structural fragility. Even going back to Shoemaker-Levy 9's spectacular impact on Jupiter in 1994, that taught us about tidal disruption and gave us a preview of what large impacts look like, improving our ability to assess impact hazards. Atlas is in this tradition. It's showing us something we didn't anticipate, challenging our models, forcing us to think more carefully about cometary physics. In 10 years, we'll probably understand what's happening, and it will seem obvious in retrospect. That's how science progresses. But here's what's different about Atlas compared to historical surprises. The implications potentially extend beyond comets themselves. Hyakutake's X-rays taught us about comets, but didn't fundamentally change our view of the solar system or the galaxy. Atlas might. If Atlas proves that interstellar comets remain active during transit, that changes astrobiology. If it demonstrates internal radioactive heating in small bodies, that changes planetary science. If it validates panspermia mechanisms, that changes our understanding of life's place in the universe. The stakes are higher with Atlas, which is part of why there's so much excitement and such intense observation campaigns. We're not just solving a puzzle about one unusual comet. We're potentially rewriting chapters of multiple scientific disciplines. We're in the home stretch now, and I want to bring this back to you personally, because I've thrown a lot of science, a lot of speculation, a lot of big ideas at you over the past 3 hours. But what does any of this actually mean for you, for your life, for how you see yourself and the world? Here's what I think. Atlas matters because it's a reminder that we live in a universe that's stranger, more wonderful, and more interconnected than we usually acknowledge in our daily lives. Most of us move through life focused on immediate concerns: work, relationships, bills, health, the news, the weather. That's natural and appropriate. Those things matter. But occasionally, it's worth stepping back and remembering the bigger context. The fact that we're conscious beings on a planet orbiting an ordinary star in a galaxy of hundreds of billions of stars, in a universe that's been evolving for nearly 14 billion years. And in that vast context, something extraordinary is happening right now. A visitor from another stellar system, carrying material that formed under alien conditions around a different sun, is passing through our cosmic neighborhood, exhibiting behavior that's forcing humanity's smartest scientists to reconsider fundamental assumptions about physics and chemistry and life itself. You don't need a PhD to appreciate how remarkable that is. You don't need to understand all the technical details about sublimation rates and deuterium ratios. The core fact is simple and profound. We're witnessing something unprecedented, and the implications ripple outward to touch the deepest questions we can ask. Where do we come from? Are we alone? What's our place in the cosmos? Atlas speaks to all of these. Let me make this even more personal. Every atom in your body was forged in a star. The carbon in your DNA, the calcium in your bones, the iron in your blood, all of it was created in stellar furnaces and scattered into space when those stars died. You are literally made of stardust. That's not a metaphor. It's documented scientific fact. But here's what Atlas adds to that story. Those atoms didn't just magically appear on Earth. They had to get here somehow. They were incorporated into the molecular cloud that collapsed to form our solar system. Yes, but where did that material come from? Some of it, possibly a lot of it, may have been delivered by comets exactly like Atlas. The water in your body, and you're about 60% water by weight, might have come from cometary impacts billions of years ago. The organic molecules that make up your cells might have been synthesized in cometary environments during interstellar journeys. The very chemistry of life might have been seeded on Earth by visitors from other stellar systems. This means your personal history doesn't start with your birth, or even with human evolution, or even with Earth's formation. Your history might extend back billions of years and across light years of space, connecting you to stars that no longer exist and to worlds you'll never see. That's simultaneously humbling and empowering. Humbling because you're part of something so vast and ancient that your individual existence is vanishingly brief. But empowering because you're not separate from the cosmos. You're an integral part of it, a way that the universe has organized itself to become self-aware. When you look up at the night sky and see stars, you're not looking at something foreign and distant. You're looking at family, at your origins, at the furnaces that created the raw materials of your existence. And when you learn about comets like Atlas, you're learning about the delivery mechanisms that brought those materials together to create you. This perspective shift, moving from seeing yourself as separate from nature to recognizing yourself as continuous with the cosmos, is transformative. It changes how you relate to the world, how you make decisions, how you prioritize what matters. Environmental destruction becomes not just a practical concern, but a kind of self-harm, damaging the systems that created and sustain you. The search for life elsewhere becomes not just curiosity, but a search for family, for other manifestations of the same universal processes that created you. The preservation of knowledge and culture becomes not just about human legacy, but about the universe's capacity to understand itself. And perhaps most importantly, recognizing your cosmic context gives perspective on the petty divisions and conflicts that dominate human affairs. The boundaries between nations, the distinctions of race and ethnicity, the religious and ideological divides, all of these shrink to insignificance when you zoom out to the scale that Atlas operates on. We're all made of the same stellar material, possibly delivered by the same cometary processes, evolved on the same world, looking up at the same sky. Our commonalities vastly outweigh our differences, but we often lose sight of that in the noise of daily life. Atlas, in its silent journey through our solar system, is a reminder that we're part of something bigger, a reminder that the universe is still surprising us, still teaching us, still revealing new wonders if we pay attention. A reminder that curiosity and wonder aren't childish indulgences, but fundamental, human capacities that connect us to the deepest truths about existence. And here's something I find deeply moving. You're alive at exactly the right moment to witness this. Atlas won't pass through our solar system again. It's on an escape trajectory, headed back into interstellar space. In a few years, it will be too faint to observe, receding into the darkness between stars. Future generations will read about it in history books, but they won't get to watch it in real time like we are. You're here now, with access to information and images and scientific analysis that would have been impossible just decades ago. You can pull up data on your phone, watch videos from astronomers observing Atlas, read the actual scientific papers as they're published. You're not a passive observer of science. You're participating in humanity's collective effort to understand the universe. That participation doesn't require a telescope or a degree. It just requires attention, curiosity, and willingness to grapple with ideas that might be unfamiliar or challenging. And by watching videos like this, by engaging with these ideas, by letting yourself wonder and question and imagine, you're fulfilling a fundamental part of what it means to be human. We're the species that looks up. We're the ones who ask why, and how, and what if. We're the ones who take the raw sensory data of photons hitting our retinas and construct elaborate models of reality, who imagine things we can't directly perceive, who build instruments to extend our senses beyond their biological limits. Atlas challenges us to do that, to stretch our imagination and our understanding. And in rising to that challenge, in following along with this investigation, even when the answers aren't clear, you're participating in something noble and ancient, the human quest to understand our place in the cosmos. So where does this leave us? After 3.5 hours of deep diving into Comet Atlas, exploring hypotheses, examining implications, what's the takeaway? The honest answer is, we still don't know exactly what's happening. As of early 2025, the mystery remains unsolved. Atlas continues to defy our best models, continues to challenge our understanding, continues to surprise us with each new observation. But that's okay. That's actually wonderful, because the mystery is what drives us forward. If we understood everything, if there were no more questions to answer, science would be finished. The fact that Atlas can still surprise us, still puzzle our best scientists, means we're still learning, still growing, still expanding the boundaries of human knowledge. Within a few years, we'll probably have the answer. Maybe it's radioactive heating. Confirmation would revolutionize our understanding of interstellar objects and possibly enable new space mission concepts. Maybe it's clathrate destabilization that would teach us about exotic ice chemistry and support panspermia mechanisms. Maybe it's something we haven't even thought of yet. That would be the most exciting outcome of all, because it would mean discovering truly new physics or chemistry. Whatever the answer turns out to be, the journey of discovering it is valuable in itself. The observations being collected, the models being developed, the debates being conducted, all of this advances science even before we reach a definitive conclusion. And beyond the specific science, Atlas reminds us of deeper truths, that the universe is stranger and more wonderful than we typically imagine, that we're connected to cosmic processes spanning light years and billions of years, that curiosity and wonder are essential human capacities worth nurturing. When you look up at the night sky tonight, if the sky is clear, think about Atlas. It's out there, invisible to your naked eyes, but visible to telescopes, moving silently through the darkness beyond Saturn's orbit, carrying secrets from another stellar system, challenging our understanding, connecting us to the broader galaxy. And remember that you're part of this story, not as a passive observer, but as an active participant in humanity's collective quest to understand reality. Your curiosity, your attention, your willingness to engage with complex ideas, these matter. They're part of how we, as a species, learn and grow and expand our understanding. The journey of discovery continues. Atlas will eventually fade from view, receding into interstellar space, but other mysteries will take its place. Other questions will demand answers. The universe is endlessly generous with wonders for those willing to look. Thank you for spending these 3.5 hours with me, exploring this cosmic mystery. Thank you for your curiosity, for your attention, for your willingness to wrestle with difficult concepts and entertain mind-bending possibilities. Keep looking up. Keep asking questions. Keep wondering. Because in doing so, you're honoring the best part of what makes us human. Our endless capacity for curiosity about the universe and our place within it. If you enjoyed this deep dive, please like this video and share it with others who might appreciate it. Subscribe for more long-form explorations of cosmic mysteries. And leave a comment sharing your thoughts. Which hypothesis do you find most compelling? What questions do you still have? What should I explore in the next deep dive? Until next time, remember, we're all made of stardust. We're all participants in cosmic processes beyond imagining, and we're living in a universe that's still full of surprises for those who pay attention. The story of Comet Atlas continues, and so does our journey of discovery.